Okay, so I've got this question set up here, right? I've put in some of the forces acting, right? So you've got this mass here, B, of 15 kilograms. So there's the weight there. And then I've got A then, the mass of that is 13 kilograms, okay? And the system's sort of held in balance and equilibrium, and then it's released, okay? So somebody's holding maybe particle B, and then all of a sudden it's released and we've got motion. Now I'm assuming in this case now, because this is the heavier mass, right? This is 15 kilograms compared to the 13 kilograms there. I think because this is heavier, this is going to go down, yeah? So this is going to accelerate downwards, and we put A here, okay? Going that way. And if B is going downwards, A will be pulled up, won't it? So, you know, it's important to have the direction of acceleration, both ends of the string, so to speak. So put it in to show exactly where we're going. And then we can use Newton's second law then, which we will in a moment, okay? We'll use Newton's second law in the direction of motion, okay? Now, before we do that, we've got to be happy with all of our forces, right? And we'll notice as well that the forces are going to be sort of resolved at an angle as well. Now, B is easily done, right? You've got the weight here and then the tension. It's all in a vertical plane, isn't it? Okay, it's nice to do that, right? You know, we're just looking at the vertical forces here because we always go, remember, in the direction of the string, right? So when we say use Newton's second law in direction of motion, okay, it's the direction of the string, okay? Now the string here, okay, is going to be moving downwards, isn't it? When B is set in motion, that's easily done. But here, okay, the string is going to be moving parallel to the plane, okay? So we got to resolve parallel to the plane. And that can cause some problems, all right? But if we're careful with our angles, then there shouldn't be any issue, okay, involved. But we must recognise that we need to resolve, yeah, in that sort of direction the string is going in there. So, you know, if we started with B here, right, it's quite straightforward because we can just simply say at B, well, we're going downwards, so in the direction of motion, you've got 15G, take away the tension, okay, that's pulling it back, and that will equal mass times acceleration, so 15 times A. That's easily done. But when we resolve here along the string, we'll have T pulling it upwards, take away then this weight which is pulling it downwards, but we need the weight resolved, right, in that direction which is parallel to the plane, right? That's what we need. Okay, so I put a sort of broken line there, a broken arrow, to sort of show that we need the resolution of the weight here. The weight is going to be holding it back, right, pulling it back, but we need to see what influence this weight has in that direction, okay, in the direction of the string. So what I always do is, I go parallel to the inclined plane there, and I go perpendicular to it, okay? And what you need to appreciate is that this angle here is going to be alpha, okay? That angle there is alpha. This angle is going to be the same as this angle, all right? That angle there, which is perpendicular, okay, this is right angles, yeah? Put right angle if you want to. That angle there is exactly the same as that angle there, okay? And if you can't see why, if you think about it, if I carried this line going down, can you see here I've got a right angle triangle, yeah? So right angle triangle, well, that would be 90, wouldn't it? And if that's alpha, how do you get that angle there? How do we get that angle there? Well, think about it. Those two angles here have to add up to 90, don't they? Because that's 90 here. That means these two have to add up to 90 to give our triangle a total of 180. So that means that there will be 90 minus alpha, isn't it? Because these two add up to 90. You know, it's whatever's left over, isn't it, from 90. So if we take away alpha, that's what you get there. That would be 90 minus alpha. And if that's 90 minus alpha, then that's got to be alpha. Because this is a right angle, yeah? This is all going to add up to 90. So if that's 90 minus alpha, this will be alpha. But just remember that that angle there, right, is always the same as that. That's all you've got to remember. And when we resolve them, we've got to appreciate then 13G, well, along here, because the angle is with it here, this will be 13G cos alpha, okay? Going back to like coplanar forces here. And then here, this will be 13G sine alpha, okay? 13G sine alpha, brilliant. Now, we've got now the component of that force along the string, okay? And you notice here, I've put down sine alpha, right? Is 5/13, okay, because that's what they give in the question. If I needed to work out cos alpha, I could use this triangle idea here, okay, because we can use Pythagoras to actually work out what cos alpha would be there. But I don't think I'm going to need it in this question, so we don't have to go down that route. What we need to do is resolve along the string. So we have T, yeah, pulling upwards. take away then the 13g sine alpha, and then that will equal to then mass times acceleration, so 13 times a. Alright, that will be at a. And then similarly then, with these two equations, 1 and 2, I need to add them, and if I add them, the t's cancel, so the 15g, and then minus the 13g sine alpha, and that these two added will be 28a. Now sine alpha I know is 5 13ths, it's given to me. So the 13s cancel, and I end up there having 15g, take away 5g is 10g, 28a. So to get a then, I'm just going to do 10 times 9.8 divided by 28, and it works out to be 35. Okay, I've done that right. I think it's 3.5, isn't it? Let me just check that. Yeah, 3.5 meters per second squared. 35 would be quite fast. So 3.5 meters per second squared. Yeah. So it's accelerating at a reasonable pace. Once you've got a, then you can work out your tension. Sub it into say 2. Okay, so sub in 2. And remember, t minus 13g, well, sine alpha is, what was sine alpha? 5 13ths equals to then 13 times a, which is 3.5. And it's just a case of rearranging that, and you get your tension, okay? So those 13s cancel, so you get 13 times 3.5, and then plus then the 5g. So I do that on my calculator, 13 times 3.5, plus then 5 times 9.8, and I get 94.5 newtons.